So today's lesson will be focusing on how radiation dose limits are established. We will be looking at things like risk, discussing the basis for establishing dose limits, defining ALARA, looking at the radiation-induced responses of concern in radiation protection, which are deterministic and stochastic effects. We'll be looking at the objectives of radiation protection, the quantities and units we use to measure radiation. Also, we'll be describing the basis of an effective dose-limiting system, explaining the rationale for occupational dose, and stating the dose limits, not just for ourselves, but for general members of the public. So what is risk? How risk is perceived will depend on the probability or the severity of the radiation effect. Risk may be defined as the probability of injury as a result of radiation. In medical imaging, risk after irradiation is viewed as the possibility of causing effects like radiogenic cancer or genetic defects. The way people look at probability and severity depends on the type and the strength of the radiation. No conclusive proof exists that low-level ionizing radiation causes a statistically significant increase in the threat of the malignancy or cancer. So although this risk may in fact be negligible, the subject is still highly controversial and of course has to be investigated. So what is a dose of radiation? When radiation energy is deposited inside the body, in the body tissues, this is referred to as radiation dose or a dose of radiation. Dose is affected by the type of the radiation, the amount and the physical properties of the actual tissue within the body, and the more energy deposited in the body, the higher the dose will be. So remember us talking about the photoelectric effect and how that contributes to the image formation. It is significant, but it also increases the absorbed dose of the body. The essential concept underlying radiation protection is that any organ in the human body is vulnerable to damage from exposure to ionizing radiation. So even though some organs are known to be more sensitive to radiation than others, every organ is at some risk because of the assumed random nature of somatic and hereditary radiation-induced effects. By somatic, I mean whole body exposure, and hereditary radiation effects in offspring from one person to the other. Now, the effective dose-limiting system includes all radiation-vulnerable human organs that are under potential risk, rather than only those human organs considered critical. So why I say this is because in earlier recommendations in the 1970s, only critical organs such as the gonads and the blood-forming organs and the bone marrow and the lungs were identified, and others were not. This has since changed, and all of the sensitive tissue that is sensitive to radiation at least, is included. Dose limits only apply to radiation received by a person that is not exposed to radiation for medical reasons, like for a diagnosis or for a treatment, or is not accidentally exposed to radiation, like a Chernobyl accident or Fukushima. So these dose limits do not apply to those people. Dose limits are applied to below the level or the threshold that biological effects would occur, and those biological effects refer to stochastic or deterministic. So once again, establishing those dose limits should be below those levels. Stochastic effects refers to the probability of having radiation-induced responses in the body. So, for example, it is a long-term effect, such as cancer may occur later on, and deterministic effects occur immediately. They are acute effects, and it's something that you are assured of obtaining. You will have a radiation skin burn after a certain dose of radiation is received to the body, or you will suffer from nausea and vomiting and hair loss as a result of a certain amount of radiation to a localized area of the body. So that is deterministic. When talking about limiting these doses and these effects, the radiation effects should always be small enough to be acceptable to the individual and to the society. So the system of radiation dose limits that is used in Canada as well as in Qatar is based on the recommendations of the ICRP, the International Commission on Radiological Protection, the organization that we discussed in a prior lesson. For the purpose of establishing dose limits, individuals are classified into two groups, and that is occupational and the radiation workers, which is ourselves, and non-occupational, which is members of the general public. So in looking at establishing dose limits, the ALARA principle is a very important concept to bear in mind. And I'm sure you all know ALARA stands for as low as reasonably achievable. The intention of this principle is to keep the radiation exposure to the lowest possible level. And the reason for keeping it to the lowest possible level is because of scientific evidence collected over the last century telling us that there is no safe level for radiation exposure. So we always have to be on the forefront of what we do, making sure that we are practicing safely and minimizing the dose for our patients when possible. ALARA does require good radiation protection practices, which are effective in keeping the average and the individual exposures for monitored workers below the limit. And our limit is 20 millisievert. For students, it is 6 millisievert at the Hamad Hospital, although the recommendations, ICRP recommendations, says that students can abide by the same limit as the public, which is a 1 millisievert per year. So radiographers and radiologists, we both share in this responsibility to keep the doses to the lowest possible level. Proper radiation safety procedures must always be performed and qualified personnel must be monitored. In keeping the dose to ourselves as low as is reasonably achievable, it is always important for us to increase our distance from the source, reduce our time whenever it's possible, and shield ourselves. So how low can you go? If radiation doses cannot be limited, there could be permanent effects on the cell, and biological changes can occur within the tissue and the organ. And these changes, as mentioned already, are stochastic and non-stochastic or deterministic effects. With deterministic effects, a threshold can be reached. When you get to that threshold or that level, you know that a radiation-induced response will occur. Whereas with stochastic effects, there is no threshold. Any amount of radiation can cause a biological effect. There is only an assumption or a probability or a best guess that radiation-induced responses may occur when it comes to stochastic effects. And these are the types of effects we try to avoid as radiation workers because we're working with radiation over years. We try to avoid these stochastic effects, which are cancer and possible hereditary effects. However, that being said, rest assured that the doses that we are working with is so low that any kind of effect is highly unlikely. So the severity of the radiation effect or the deterministic effect depends on the amount of radiation dose received and the period of time over which the dose is received. A very high dose to the whole body can cause sufficient damage to the organs and lead to possible death. And radiation sickness is an early deterministic effect due to an acute high dose of radiation to the body. Early effects, like mentioned before, is erythema or it could be sterility, which occurs at 150 plus millisievert, around about there, or it could be cataract inflammation, which results at 3,500 millisievert range. As you can see, these doses are quite high. With stochastic effects, the amount of radiation does not change the severity of the effect, but it does alter the chance of getting cancer down the line, or mutations of cells, or alteration of cells. So, for example, exposure to high dose can increase the risk of the cancer, but if cancer does occur, the severity of the cancer is the same as if, you got a cancer just randomly without ever having to deal with radiation. So it's basically like a lottery, because there's a 1 in a million chance you may get it. So with stochastic effects, the cell is damaged and may be altered over time, but there is no observable effect or immediate effect that can be seen. So what must we protect ourselves from? And that is the whole objective of radiation protection. We need to protect ourselves from deterministic and stochastic effects. We need to prevent radiation-inducing deterministic effects from occurring by following dose limits. And we need to minimize stochastic effects by using radiation protection and using the least amount of radiation that will produce an optimal image. Remember, we, the medical radiographers, are responsible for patient safety from radiation, and since we are also subject to exposure ourselves, it's our responsibility to be familiar with the ICRP dose limiting guidelines. An effective dose-limiting system is used to assess radiation exposure and any associated biological damage to the workers, ourselves, as well as to non-occupational workers, which is the public. And there are separate limits for both. So dose limits do not include natural background, and it does not include medical exposures. So how do we assess radiation exposure and its relative biological damage? Dose assessment quantities that must be taken into consideration include the nature of the ionizing radiation, the strength of the source, the biological sensitivity of the area exposed, and also the exposure factors and the time, distance, and shielding from the source. There are various radiation quantities and units, as you can see here. Calculation of these quantities form part of an effective dose-limiting system that can be used to assess various risks of cancer and genetic effects to the tissue or the organ exposed to radiation. The activity of a source of radiation can be measured in becquerel, which is 1 disintegration of a particle of radiation per second. Becquerel is a SI unit or standard international unit used to measure activity. And then we have exposure. Exposure is the quantity of a radiation, the amount of ionizing radiation that strikes the patient's body or the object. And exposure can be measured using an ionization chamber. Exposure is the total charge given in 1 centimeter of air by ionizing the air with X-rays or gamma rays, for example. And the unit of measurement is coulombs per kilogram, which is also a standard international unit. So let's look at exposure and activity closely over here. And here you can see that this person on the left is getting exposed by a quantity of radiation or a quantity of radioactive substance. Like I mentioned before, these levels of ionization or radioactivity can be measured with an ionization chamber. And it is the total charge given in 1 centimeter of air by the ionizing radiation. The intensity of the radiation or its activity is measured in units of becquerel, as already mentioned, and this is in the form of 1 disintegration per second. When ionizing radiation penetrates the human body or an object, it deposits its energy per unit mass within the body. The energy is absorbed from exposure to radiation and is therefore called absorbed dose. So the absorbed dose is measured in a unit called gray, and a dose of 1 gray is equivalent to a unit of energy, which is joule, deposited in the kilogram of the substance. Absorbed dose is cumulative, so it doesn't really matter what type of radiation you're dealing with. You could be dealing with 5 or 6 different types. All you have to do is add them up to find out what the absorbed dose would be. So here you have a problem to solve. You have an exposure to a patient. This patient received 1 milligray of gamma. She received 14 milligrays of beta and 5 milligray of neutron particles. What is her absorbed dose? So simply, the only way to solve this problem is to add all of them up, and that will give you the milligray of absorbed dose. So now let's look at equivalent dose. When radiation is absorbed in the living matter or the material, a biological effect may be observed. However, equal absorbed doses will not necessarily produce equal biological effects. The effect is going to depend on the type of radiation. Was the person exposed to alpha, beta, or gamma? Now, before we worked out what the absorbed dose was, now we need to add to that what the effect of each type of radiation would be. For example, 1 gray of alpha radiation is more harmful to a given tissue than 1 gray of beta radiation, perhaps. To obtain the equivalent dose, the absorbed dose is multiplied by a specified radiation weighting or a quality factor for that particular type of radiation. So the radiation weighting factor or the quality factor represents the different types of radiation that has different biological effectiveness. The equivalent dose is expressed in a measure called the sievert. That is the SI unit of measurement. The greater the rate at which the radiation transfers energy to the tissue, the greater the biological damage will be. And so these radiation weighting factors, they give that some relevance. The term equivalent dose was introduced to reflect the different biological effects of the different radiation types. The equivalent dose is calculated by multiplying the absorbed dose by the radiation weighting factor. Now I want you to take a few minutes and try and solve the problems to the right of this slide, questions 1 and 2, and then I'll meet you back here in 10 minutes. See you then.